A good weekend. Um, we finished up early on Thursday, so I sent out the link to the Chapter 3 video on numerical methods. It's, I don't know, 40 minutes long or something, which goes through the big three numerical methods. There's links in the content on Blackboard that goes you to these different solvers. Uh, Basically, what's nice about that, I like to do that because a lot of these applications we talked about, the ones that we talked about, all have nice little elegant solutions, but many of them do not. And so that's when you would bust out the numerical methods. And I really like it because it takes it back to the geometry we talked about on the first day of class with slope fields. The first derivative at the end of the day gives you a slope. So if you have an initial condition, you can build your solution numerically by guessing and checking and doing trajectories with slopes. So that's what Chapter 3 is all about, is how you numerically program that for a couple different methods. And as you'll see, if you've watched the video, you know this already. If you haven't, you'll see that a couple of those methods, if you're just trying to solve the basic diffEq, and we'll talk about another basic one today. If you're just trying to solve this basic differential equation, with the integral here, that those methods that we talk about correspond to the right endpoint sum, the trapezoidal rule, and Simpson's rule. So that's kind of a nice little callback there in that video. So make sure you watch the Chapter 3 video. You've got your take home 4 and test 4 due on Wednesday, and then there is no test 5. Test 5, you're just going to have a 50-point take home. So if you had me in Calc 3, once in a while this happens. You just have a big take home instead of a test, and you'll see why. The first question is a numerical question, and then the second question, it just takes you through a mathematical model, solving it, an important one. So, okay, so that means that pretty much the scope of work for us this week is working on getting into Chapter 5, which talks about second order differential equations. So we're going to focus primarily on linear equations. So let's define those. We had linear first order equations. Could be written in the form y prime plus p of xy equals f of x. So if we go up in order, right, second order means we're going to have second derivatives running around. So y double prime plus p of xy prime plus q of xy equal f of x. This would be the form you try to put it into to prove it's linear. Notice that the function y and all of its derivatives are to the first power. The coefficients and the non-homogeneous term depend at most on x. They don't depend on y. Okay, so these are the creatures we'll be looking at, and actually we're going to spend most of our time looking at constant coefficient equations, where the p and the q are real numbers and don't have any x's in them at all. So that's kind of what we're looking at here. But as a run up to this, we're going to need to borrow some results from algebra, in particular linear algebra. So if you had Calc 3, you've already had a little reminder about what a determinant of a 2x2 matrix is. If you have not had Calc 3, there's a chance you might not know what these determinants are. I'll check with Paul to see when he gets into determinants, because they feature, at least as some nice theoretical tools in linear algebra. But here's how you get it. Here's what it is. A 2x2 matrix is just a 2x2 array of numbers. And we use this notation of these vertical bars, which indicates we're taking this matrix and we're going to associate a number with it. And the way you calculate a 2x2 determinant is you multiply a times d and then subtract off b times c, and this will give you a number. So the determinant takes a 2x2 matrix and spits out a number. So this example here, 4 times 1 minus negative 3 times 2. 4 times 1 is 4 minus a negative 6. That's 4 plus 6 is 10. Okay. Now, one of the things you can do with determinants is you can prove a result called Cramer's rule. Cramer's rule is a way to solve systems of linear equations in terms of determinants. This is a very inefficient method to do it. So Cramer's rule is one of those things where, I mean, we'll be using it today, you know, little 2x2 cases, as a means to an end. Okay, so this theorem is one of those things. It's kind of like back in Calc 3 when we talked about stuff in Calc 3 with that arc length parameter. It theoretically was a nice thing to use to define and describe things, but practically it was kind of cumbersome to work with. That's kind of the same thing with Cramer's rule. It's theoretically it's a nice result. It's going to help us prove what we need to do here in differential equations, but usually you'll find more efficient methods to solve systems. So here's what it says. You got a system of linear equations, ax plus by equals e. Yeah, exactly, Zoran. Yep. And cx plus dy is f has a unique solution provided this determinant is not 0. So a, c, b, d, this is called the coefficient, determinant of the coefficient matrix. The way you get it is the first column are the coefficient of x's, and the second column is the coefficient of y's. Right? So as long as the determinant isn't 0, not only is there an answer, there's a unique answer. There's only one answer. So unique, remember, means only one solution. And the way you can use determinants to get that solution is we take this d, and what we do, d1, we replace the x column with the constants, and then we keep the y column, the coefficients of y. So replacing the x with the constants and dividing d1 by d, since we know d isn't 0, that'll give us our x value. And then for d2, what we do is we keep the x column the same and replace the y with the constants. And then y is d2 over d. So that's the method. We're going to do an example here, and we'll do some more examples as we move through this section. So use Cramer's rule to solve this equation. And we'll remind you what this means graphically. But if we just go through the algorithm here, we calculate the determinant d, the determinant of the coefficient matrix. So we're going to have two columns here, x and y. Into the x column, we put the coefficients of x, so 3 and 2. Into the y column, we put the coefficients of y, positive 7, positive 12. And then we go through, as my one former student Eric used to say, the zig minus the zag. So that's how he liked to think about this. So 3 times the 12 minus 7 times 2. So you get 36 minus 14, which is 22. And what's important for us about 22 is that it is not equal to 0. So we are guaranteed one and only one solution. So what is that solution? Well, for D1, what we're going to do is we're going to replace the x column with the constants. We'll keep the y column as the coefficients of y. So the constants here in order are 5, negative 2. And now we'll do the zig minus the zag. So that's 60 plus 14. That's our 74. So this gives us our x. X is d1 over d, 74 over 22, which is a common factor of 2 there to give you 37 over 11. And now to get the y, I'm going to just keep that d there. To get the y, we're going to swap out the y column for the constant. So we're going to get d2. X column, coefficients of x. The y column will be the constants. 5 negative 2. 3 times negative 2 minus 5 times 2. You get a negative 6 minus 10, negative 16. And so the y equals d2 over d, negative 16 over 22 minus 8/11. Right? So algebraically, we typically express the solution to this system as a pair. So we got 37/11, comma, negative 8/11. Algebraically, this means that if you substitute in 37/11 for x and negative 8/11 for y, both equations are satisfied. So 3x plus 7y will give you 5, and 2x plus 12y equal negative 2. Does anyone remember what this means geometrically? So if I wanted to check graphically, what I'd be looking for here? So I got 3x plus 7y is 5. 2x plus 12y is negative 2. And if I plot the point, what's going to happen here? If I plot that pair, 37/11, comma, was it negative 8/11? Boom. That's exactly where these two lines do what? Yeah, that's where they intersect. Yep. So you got x and y satisfying both equations. That means that coordinate point, or that point rather, is on the graph of both lines, so it's an intersection point. Okay, that's a little review there. Once again, this is a fairly inefficient method. You could also do substitution elimination. When it comes to solving these systems, on your homework, you basically pick whichever method makes most sense to you. Okay. All right, so now we're going to see this version of Cramer's rule pop up in the work we do today. So let's look at a second order initial value problem. So this is the second order linear equation that we talked about. To make it an IVP, an initial value problem, we need to have initial conditions. Now, if you think about solving a second order equation, just like a basic one, like y prime equals, I don't know, sine of x. And you want to figure out what y is. You know that y double prime is sine. You can start working towards what y equals by doing what to both sides? Yeah, you integrate. So y prime would be the integral of sine x dx, which will give you minus cosine x plus a constant. And then to get from y prime to y, I would integrate again. So that's the integral of minus cosine of x plus c1 dx. So minus sine x plus c1x. But then, since we've integrated twice, I'm going to pick up another what? Constant. Okay. And since we've done successive integrations, these, you can't really combine these constants, right? They're not like terms or anything. The C1 came from the first integration. The C2 came from the second integration. So just like with first order equations, we kind of expected to have one parameter solutions. In other words, one arbitrary constant floating around, because ostensibly there's one integration happening to solve it. When we have second order equations, there's two integrations that are going to happen. So we're going to expect to have a two parameter family of solutions. Does that make sense? So two constants, two parameter families. So in order to pin down these C1s and C2s, if we're going to have an initial condition, remember initial conditions talk about what's happening at a particular point. So our initial conditions are going to be of the form I just want to be consistent with the book. Y at x naught is k naught. Y prime at x naught is k1. So the key here, once again, remember, for initial conditions, we're looking at the value of the function and the derivative at the same x value. Now what this does for us geometrically, if I'm graphing my solution here, so y at x naught equals k naught, that gives us a particular point. That gives us a particular point that the solution curve is going to go through. What does y prime give us? So y geometrically gives us the actual location on the graph. Y prime is going to give us the what? Yeah, the slope. So here the slope is k1, and that's what we're going to need to do to help us pin this down, right? So in the grand scheme of things, right, the y prime has one constant, so the y prime at x naught is k1 is going to help us figure out the c1. Once we know the c1, then we can plug the initial value in here. Right. So far so good, folks. Does all this seem to make sense? And so the existence and uniqueness theorem, which we're not going to prove this. If you wanted to, this would be a great project, actually, to see how you can kind of bootstrap the proof we did for first order into second order. And, how are they the same? How are they different? That's a great project. But as long as your coefficient functions, p and q, and your non-homogeneous function, f of x, as long as p, q, and f are continuous in an open interval containing x naught, then you're guaranteed one and only one solution. All right? So it's just the extension of the theorem we had for first order. Okay, recall, a linear ODE is called homogeneous if f of x equals 0. In other words, this is a homogeneous second order linear equation. And we have a function that will work for this, right? If I look at the function y equals 0, then certainly y double prime plus p of x y prime plus q of x y is all going to be 0. So this is called the trivial solution. Because you take the derivative of 0, you just get zeros, and zeros times anything is 0, and add up a bunch of zeros, you get 0. That's called the trivial solution. Now, if p and q are continuous and you impose initial conditions, y at x naught is 0, y prime at x naught is 0, then the only solution is the trivial solution. Because y equals 0 certainly satisfies all that information. It satisfies the diffie q, it satisfies the initial conditions. And since there's only one solution, then it's got to be the 0 solution. So that's how that existence and uniqueness theorem kicks in. That's what we talk about here. Okay. All right, let's take a look at this next example. So the goal here now over the next couple of examples is to work towards a more general theory of homogeneous equations. All right. And once again, if you're in linear algebra, you've likely, well, I don't know, you're a month into linear algebra now. So you've likely talked about homogeneous systems of equations. So if you're in linear algebra right now, or if you've read linear algebra or whatever, a lot of this is going to have echoes of linear algebra in it. All right, so we're going to be working with this differential equation: y double prime minus y prime minus 12y is 0. And apparently my phone is somewhere near here. Apologize for that. And we're asked to show that y1 equals e to the minus 3x and y2 equals e to the 4x are both non-trivial solutions. So the non-trivial part, remember, that just means that these functions aren't identically 0. And in fact, not only are these functions not identically 0, each of these are never 0, right? Because e to the whatever is always a positive number. So that's the complete opposite of well, I shouldn't say that. Trivial means always 0. Non-trivial means at least sometimes not 0. These folks are just never 0. So we'll go through the y1 case, and then I'll leave the y2 case for you. But if we want to show that these are solutions to the DE, what that means is, going back to day 1, it means if we plug this into the diffie-q, we're going to get 0 out. So we just go through here. We'll get into Dirac delta. That's like the second to last lectures are on. But yeah, a solution, I've never seen it as a solution. The Dirac delta, when we see it in this course, the Dirac delta is going to be something we put over here. The Dirac delta will be put over here, and then that gives us the Heaviside function. But yeah, we'll get the Dirac. We'll talk about that, because technically it's a distribution at the end of the course. But yeah. So every time you take a derivative of this exponential, you're just going to be multiplying by -3. And so now I just stuff this in, y1 double prime minus y1 prime minus 12y1, I don't know, does it equal 0? Let's find out. 9e to the minus 3x minus -3e to the minus 3x minus 12 e to the minus 3x. Well, you got 9 plus 3 minus 12. By golly, that's equal to 0. Okay. So it's a non-trivial solution because it's not identically 0 and it satisfies differential equation. I'll leave it to you to work through the details with y2 equals e to the 4x in the privacy of your own home. Okay. Show that c1 e to the minus 3x plus c2 e to the 4x is also a solution for any choice of constants c1 and c2. All right. So we've seen this kind of construction before when we were talking about when we proved the existence and uniqueness of linear solutions a couple of weeks ago. Do you remember what we called this when we took constant multiples of functions and added them together? This is later on in the handout too. This is called a linear combination. Of y1 and y2. It's a linear combination, linear combo. Because we're keeping y1 and y2 to the first power, we're just multiplying by constants and adding them together. You might also recognize this as a two-parameter family going back to week 1. Okay, this is a basically we're showing that this is a 2-parameter family of solutions. All right, so once again, now you can see why I'm going to let you do the e to the 4x in the privacy of your own home, because this actually kind of does both. So what we do here is we start with our function y, and we just go through, take the derivatives. Every time you take a derivative of e to the 3x, you're going to be popping out a multiple of -3. And likewise, every time you take a derivative of e to the 4x, you're going to be popping out a multiple of what? 4. And so now we'll do it again. Hopefully this is an easy way to move into the week here for us in DiffyQ. Just taking derivatives of exponential functions. Get it? Easy. All right. Now we stuff this in. Y double prime minus y prime minus 12y. Is that going to equal 0? Let's find out. Got my 9c1 e to the minus 3x plus 16c2 e to the 4x minus -3c1 e to the minus 3x plus 4c2 e to the 4x plus 12 c1 e to the minus 3x plus c2 e to the 4x. Does that equal 0? So let's take a look at the e to the minus 3x terms here. We've got 9c1 of them from there minus a -3. That's going to give us plus 3c1 of them there. Oops, this is a minus 12. Hold on. Helps if you plug it into the right equation. So we're going to have 9c1 plus 3c1. This will give us minus 12c1. So 9 plus 3 is 12c1 minus 12c1. So that'll zero out. So these will be gone. Now we look at do the same thing with the e to the 4x's here. We got 16c2 of them. Here we have a minus 4 of them. And then a minus 12 of them. So sure enough, 16 minus 4 minus 12, those are going to zero out as well. And by golly, that's equal to 0. All right. So not only is e to the minus 3x and e to the 4x solutions individually, any linear combination will be as well. So you could actually, if you just pick, for example, if you pick c1 as 0 and c2 equals 1, then you actually recover e to the 4x. So when you have a linear combination of two functions, you always recover the individual functions. You always choose like c1 to be 1 and c2 to be 0. You can always recover sort of the original building blocks there. Okay, so the original functions will always be specific cases of the linear combination, so it includes them. All right, so it's kind of like you got a bunch of Legos, right? You got these two Lego blocks and you're just building them together. It's kind of like the basic ingredients. When I teach linear algebra, which hasn't been for years, these types of functions are like ingredients. You've got flour and sugar, and now you can combine different amounts of those things to make different things. You follow? So that's kind of how of course it's a food analogy. Of course it is with me. Okay. So we know that this will work as a solution to the DiffyQ. Now the question is, let's find C1 and C2 so that we get a solution to the following initial value problems. So we're going to start off with our y1. So, excuse me, there's our function y. We know that y at 0 is 2. So you plug in there. E to the 0 is 1. And now I need to know what y prime is. I need to, because I need to plug that in. So I look at y prime at 0. And that's supposed to be negative 1. Oh, I guess I should do this proper. So y prime at 0 is negative 1, so I plug that in there. Okay. And by golly, look what I got. I'm trying to figure out what C1 and C2 are. I have 2 unknowns, but I have 2 equations. Look what I have. This takes us back to the top of the hour. That's a system of linear equations with the unknowns C1 and C2. Once again, you can solve this a variety of ways. I'm going to use Cramer's rule. And with the disclaimer, in case the folks in linear class, this gets back to Zachlin, I'm using Cramer's rule all the time. It's a means to a theoretical end. All right. All right. So we would go through Cramer's rule. We'd look at the D. The unknowns here are not X and Y, rather C1 and C2. So I'd have a column for C1, a column for C2. What are the coefficients of C1 here? There's no number. Yeah, so it's 1 and negative 3. Very good. What are the coefficients of C2 here? Very good. 1 and 4. I do the Eric zig minus zag. 4 minus negative 3. That's going to give you 7. And what's important about the number 7? It sure as heck isn't what? 0. That means we're guaranteed a unique solution. So we'll go through the D1 here. The D1, we replace the C1 with the constants, and we keep the coefficients of C2 as is. So I do the zig minus zag. I get 2 times 4 is 8 minus a negative 1. That gives me a positive 9. D2, we'll keep the C1 coefficients the same. We'll place the C2s with the constants. Do the zig minus the zag. Negative 1 minus negative 6. So we get, what, a 5 out of that? And so I can get C1 is 9/7 and C2 is 5/7. Any questions on the calculations there? So then the last step then is to write down the solution to the IVP. Y equals C1 e to the minus 3x plus C2 e to the 4x. C1 we found was 9/7 e to the minus 3x. C2 was 5/7 e to the 4x. And if all goes well, that's what matches the handout. There it is. Okay. Now, I'll leave this one for you to do, but let's just talk about what's different. Here's y at 1 is 2. Y prime at 1 is negative 3. So what would be different in our solution methodology? Instead of plugging in 0, we'd be plugging in what? For this one here. You'd be plugging in 1. So it'd be y at 1 is 2, and y prime at 1 is negative 3. And we would just get different coefficients for C1 and C2. You follow? But the process would be identical. The process would be identical. Okay? So I'll let you go through that. Consider this part of your homework just to check to make sure you can do the Cramer's rule. To see what's going on with that. Because we want to end today with proving that this is the general solution to any initial value problem. So once again, what's it mean to be the general solution? So the general solution means that this linear combination, this two-parameter family of solutions, contains all the solutions to any initial value problem. We've shown that this satisfies the Diffie-Q. We also have existence and uniqueness, since the coefficient functions here, and these are all constants, they're all continuous. We know that there's a unique solution. So all we really have to do at this point is to show that we can always find a C1 and a C2 that's going to satisfy the initial conditions. Since y double prime minus y prime minus 12y equals 0 satisfies the existence and uniqueness theorem, because the p of x is a minus 1, the q of x is a minus 12, and the f of x is 0, are all continuous everywhere. And y equals c1 e to the minus 3x plus c2 e to the 4x is a solution to the differential equation part. We just need to show we can find C1 and C2 to satisfy the initial conditions. Y at 0 is k naught, excuse me, y at x naught is k naught, y prime at x naught is k1. Once we do that, we're done, because then we found a C1 and C2 that satisfies the initial conditions. By the existence and uniqueness theorem, that's it. That's the definite article, the only one. That's the only solution. Okay? So how are we going to do that? Well, we're going to use Cramer's rule. We're going to start off with our function. We're going to do the exact same process we did before, just generically. All right, so I'm going to impose the condition y at x naught is k naught. So I'm just going to plug in x naught for x. And now I'm going to look at y prime. As we saw this, once again, hopefully you realize this is the exact same process we did just a few minutes ago. We just are plugging in x naughts and getting out, k's. And even though these e to the minus stuff, even though these exponential things look like functions, they're not. They're numbers. We've plugged a number in. The one we did together, we plugged in 0, so the e to the 0 was 1. It simplified nicely for us. But at the end of the day, this is the system of equations we have. We've got e to the minus 3x naught c1 plus e to the 4x naught c2. That has to add up to k naught. And we've got negative 3 e to the minus 3x naught c1 plus 4 e to the 4x naught c2 equals k1. And here's where we use Cramer's rule. Whoops. Because I know that I get a unique solution to this system for C1 and C2. Remember, these are the constants we're trying to find. The x naught and the k naught and k1 are given to us. This has a unique solution as long as that determinant d isn't 0. So let's calculate what d is. So d, coefficient of C1s, coefficient of C2s. What's the coefficient of C1s here? So once again, the x naught is a number. We've plugged that in. So what's the coefficient of C1 in the first equation? What's the number multiplying it? No. So look in the equation here. Here's C1. The coefficient is actually this number, whatever that is. Because remember, the x naught's going to be given to us to get plugged in. Likewise, what's the coefficient of C1 in the second equation? It's, minus 3e to the minus 3x naught. And then for C2, the coefficient here is e to the 4x naught. And here it's 4e to the 4x naught. Once again, in the generic situation, the x naught's given to us. It gets plugged in, just like we plugged in the 0 for the scenario we did just a little bit ago. So now let's do the zig minus zag on this. I've got e to the minus 3x naught times 4e to the 4x naught minus e to the 4x naught times negative 3x naught. And now we're going to simplify this. So in the first term, we've got 4 e to the minus 3x naught e to the 4x naught minus a negative 3, so plus 3 e to the minus 3x naught e to the 4x naught. So now we got to go back, do a little algebra here. If you have the same base, what do you do with the exponents? Add them up. So this is sort of the reverse of the property we've been using a lot in diffie-q. So 4e to the x naught plus 3e to the x naught gives me a total of how many e to the x naught? 7. And I don't know what x naught is, but I know that e to the anything is never what? Yep, so if this is always positive, then 7 times this, that's going to never ever be 0. And so Cramer's rule kicks in. says that there's only one solution, right? So Cramer's rule is a existence and uniqueness theorem for that system of linear equations. This tells us that no matter what we pick for x0, k0, and k1, we're guaranteed a unique solution for C1 and C2 that's going to match those initial conditions. Okay? Now, if you look back at this determinant, and you know, I think this is what 3 with the coefficients. If you just go in there and erase that x0 there, then you see we've got y1 and then y1's derivative, right? And then y2 and y2's derivative. This motivates the definition of what's called the Wronskian. And this is the character we'll be talking about here for the next couple of days. This is going to help us determine when we get different enough answers to a differential equation that they can be used to write the general solution, right? So that's what we're after. Is we're after trying to figure out when we can get the general solution. All right. So there's going to be a fair amount of theory and some practice as we go through, which I think is appropriate because it's a sophomore level course, right? So a sophomore level differential equation course should include not only how to do it, but like why the stuff happens. I think you saw that hopefully in chapter 2 when we took the time to go through some of these proofs and derivations in detail. You know, hopefully some of it sticks, or if it doesn't quite stick, at least when you see it again, like in a later course, it's not unfamiliar, right? I still remember when I got to some of the upper level math, you know, I was kind of shell shocked in some classes, but in other ones I wasn't so much because the instructors had gone through some of the more theoretical stuff. So that's what we're doing. And especially if you're in linear algebra or have done some reading in linear algebra, you know, hopefully you'll start to make connections between the two classes. Okay. All right, that's all. That's it for today. Have a great rest of your Monday, and we'll see you back here tomorrow.